factor out a negative. Good. And that's like negative x squared minus 4x.
Oh, I remember this. And then you.
It's high level algebra. Yeah, and then you leave a little blank space over there. Okay, what number goes here? 4. What have I just done? I've just subtracted 4, Ward's VJ, so I must like add 4 back in order to like make it like be correct. Okay, so then what's going on here then? This becomes like 2 dx over, make this like pretty in the bottom, it's the square root of yeah, it's like 4 minus x minus 2 squared. Alright, now do you have any ideas? What are your ideas? Berkowitz. Yeah, it's arcsine. Berkowitz sees that this is effectively more or less just arcsine in disguise. And in fact, there are many ways to like proceed from here, but to me, it's helpful to get rid of that x minus 2 because it's like kind of annoying. So I'm just going to do a quick substitution of u as x minus 2, and du is dx. Some people don't like to do this, but I think it's always a good idea because it helps me just keep everything nice and clean. So then what does this thing turn out to be? It's like 2 dx is just du over root 4 minus u squared. Alright, and now that's like very arcsine looking. Do you guys get it?
Yeah.
Okay, cool. What's the only problem?
4.
That 4 like needs to be a 1. So how can we make it a 1? Alright, keep going. Do it. Factor out of 4, like inside the radical. Alright, you're totally screwed. You're last. You need to drop out of the classes and catch up on Kevin's. Good. Alright, then you can pull that 4 out of jail, and then that just cancels with the 2 on the outside, yeah? Okay, and then you can also just sort of like rewrite it as du over root 1 minus, and like what's important is that we do that kind of like please thing again, right? Right, just says like that. Alright, now it's like really arcsine looking. Very strange. Cool. Okay, and now I always go all the way to the bitter end, so I'm going to do one more substitution, pick whatever variable you like. I like to go to W here. Just look like you. I'm missing the 1/2, so I stick in the 1/2, and I undo the damage with the 2. Finally, I have been able to write the whole thing out as a straight arcsine problem. And I never anti-differentiate until I get all the way down to the base formula. Some people like to do some of this in their head, but I don't know, I just feel like it's too easy to like make all kinds of little mistakes. Anyway, answer 2 arcsine W plus C, but really W is just U over 2 and U is just that. So the actual final answer, 2 arcsine x minus 2 over 2 plus C. Cool. Alright, how are we doing? Got this? Okay, good. Alright, please do another problem right now. Do 25. You got 5 minutes.
I think there's going to be a rapid. Okay, go.
So it's like 1/3 dx over x minus x over root 3 quantities.
Why'd you take 3? Oh, yeah. Like the dot. Wait, or do you take a 3 out to kill? No, you definitely take a 1/3.
2 is substitute out.
So you W like you over. That's right. But that's a first target.
If you substitute on the W, you know how to do AW equals the mod U. When you do that, you're going to get 2.
Yeah, but we're gonna go here.
Or is it root 2 over 6? Yeah, W equals.
So they're root 3 on top. No. I know there's no. I just want to. You like have to like have like a root 3 like you don't want to root 3. So go right there. Yeah.
Cool. Are we cool? Alright. Like I said, some people just pick this up right away. Other people have some struggle with it a little bit. Oh, other people, you're here. Cool. Oh yeah, I forgot to say. Perfect timing. Alright, take like a minute-ish or so and wrap up, and then we're gonna switch to a different topic for the second half of class. Cool, feeling good? This table under control? Are you gonna teach know how to do this? Figure this out? Do you like read the book or just knew this already or watch the videos or something?
I just solve problems.
Good time.
Alright. Good. Wrap up whatever problem you're on and we'll oh yeah, also don't go past page 6 because we'll do the rest of those we'll do those in class together also. Alright. Are those like real strawberries? Well, so like they were once fruit. Alright, good. Yeah, we should probably like turn the camera. Yeah. Camera person. Pick it back up again and put it over back there where your real seat is. Or not. Or just leave it there, it's fine. Whatever. As long as you can see it's good. Good. We're changing now to a totally different topic. On the first day of this class, actually I changed my mind, I want to vote. On the first day of this class, we talked about calculus and we discussed what calculus really is. What is calculus really?
It's like these two hard problems.
It's like these two hard problems. Yeah, what were those two hard problems? The tangent line problem. And the other one?
No.
The area problem, yeah. And the tangent line problem was the problem of trying to find the slope of the tangent line to a curve. And the point, what was the point of the tangent line problem again? Why did we care about that? Yeah, you want to know how fast you're going, right? Basically, if you can find the slope of the tangent line to an arbitrary curve, then you can know, how fast you're going, or the rate of change of a function at a given point. Okay, then there was the area problem. It's been a long time, so like, what is the area problem, and like, why do we care about it? Somebody. La, 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 la. Yeah, what's the area problem?
It's the area under a curve.
Yeah, find the area under a curve. Why do we care about the area problem, Reynolds?
Mr. Schaefer was like,
Oh. Yeah.
if we take the area under an acceleration curve, we get the velocity.
Yeah, or maybe even more straightforwardly, because I think we did this also in the first day of school, right? If you have a, that example works too, but it's a little like abstract. If you have a velocity versus time curve, and I don't know, you start around here at like 1 o'clock or whatever, and for an hour you go at a certain speed, and then at 2 p.m. you switch to going at a different speed, and then at 3 p.m. you switch to going at another speed, and at 5 p.m. you just like stop. Okay, so these 3 lines are like my velocity function. And now the question is, how much total distance did I travel? Well, if I think of the area under this curve, well then I just have a bunch of rectangles. And if I kind of look at these rectangles one at a time and try to interpret them, then it's clear that they're just distances. Because I was going like at this velocity for this amount of time. And so when I multiply the length of that time interval times the velocity I was going during that time interval, then I get the total distance traveled. Yeah? Just like so clear. And then from from 2 p.m. to 3 p.m., that's an hour that went by, and during that hour I was going at a certain velocity, so when I multiply the height of that rectangle by the width of that rectangle, that gives me the distance traveled over that interval. And then finally, if I multiply the speed I was going from 3 p.m. to 5 p.m. by the length of time I was going that speed, which is 2, then I get the area of this rectangle, and that represents the distance traveled. Cool? I got that. So where it gets kind of like weird and interesting and also hard is if I have not a constant velocity curve, but like some variable velocity curve. So now let's suppose that I was traveling from 1 p.m. to 5 p.m. Via some velocity curve which is changing, that's not like a step function. Well, now I still want to know how much total distance have I traveled. And we can still calculate that, but now we have to kind of like estimate it or something. So we have to just kind of be like, well, during that first hour, I was kind of going that fast-ish. Not really. Truly, I was going most of that hour, I was going faster than I was going, than this rectangle would suggest, but it could be worse. And then during the second hour, the height of this rectangle represents approximately how fast I was going. And then during the third hour, the height of this rectangle represents approximately how fast I was going. And over the fourth hour, this rectangle represents approximately how fast I was going. So the heights of these rectangles are kind of like the speed that I was going during those various intervals. Hold on. And now, if I pick the area of this rectangle, I get a time multiplied by the amount, the velocity that I was going during that time, which gives me roughly the distance traveled. And same here, and same here, and same here. So if I add all 4 of them up, that will give me an approximation to the true distance traveled. Get it? Okay, so of course, the more rectangles, the better the approximation. And if I could somehow find the exact area under that curve, then I feel like that would give me exactly the distance traveled. Good? Yo.
What?
So much to say about this, but.
What do you get when you like anti-differentiated position?
Okay, good. Stop. All right, good. All right, good. So now let's actually do it. There is a Jordan. Can you grab that packet behind you? All those. Yeah. Can you like what I want the actual packets? Actually, I want to have them. Can you like pass them out like super fast? Okay. Good. So let's do a whole problem over here. And Hannah, your head is sort of directly. Yeah. Okay. Good. So what's coming around to you right now? From Jordan is a problem that we're all going to do together. And there are many, many different ways to do this, so don't complain. Just like, let's all do it the same way, just because. This is a quadratic. The quadratic has come pre-graphed for you, so let me just graph it right now. And just like read the little paragraph on the top that explains what it is that we're trying to do. Thank you.
Wait, no, I would get
So goal, approximate the area of the region which is bounded by the x-axis, this function, and the lines x equals 0 and x equals 2. So in a very, very light pencil shading, can you shade the region that we're trying to find the area of, just so we all agree that we know what we're all talking about? It's like that, right? So goal of this page, kind of, is to find the area of that green shaded region. Okay, how can we do this? Well, we're going to use rectangles. And in fact, the prompt sort of even says like how we're going to do it, right? Divide the interval from 0 to 2 up into 5 equal width subintervals and approximate the areas using rectangles that lie below and above. All right, if we want a lower estimate, lower first. If we want a lower estimate, how should we draw the rectangles? Draw rectangles in such that the area of those rectangles gives us a lower estimate. And look at the person next to you to make sure they're doing it right. Alright, so these are the 5 rectangles that I drew. You guys with me? Most people just draw these 5 just kind of by common sense. But if you want a little explanation of what I was thinking as well, I want a lower estimate. So I want my rectangles to live like below the curve for starters. Now, I mean, Shiv, I could be silly and just draw some really short rectangle like way over here, right? That would be an underestimate. But I kind of wanted to like have some connection to the actual function. And so I sort of drew in some ways what I did was to draw the rectangle which is the shortest that it can be while still like agreeing with the function for some point on that subinterval. These are called subintervals. The entire interval from 0 to 2 we just called the interval, and I said to split up into 5 subintervals. So actually, what are all these numbers? This would be like 0.4, or maybe we just say 2/5, 4/5, 6/5, 8/5, like so. Okay, cool. And yeah, okay, so cool. Say cool. Right. now our goal is we want to find the area of all these 5 rectangles. If I just left you alone for a minute or two, you could probably just do it, but instead let's kind of pursue a sort of systematic approach that will like generalize. So alright, let's like label these points over here where the rectangles are touching the function. So this point, what's this x? What are these x and y coordinates? Eve, what's the first one? Wait, hold on, look up here. It's just x coordinate? Yeah, it's 0.4. I'll write it as 2/5. Y coordinate, let's just be lazy and write f of 2/5. Because I don't care right now what it is. Okay, Eve, next one. What's this point?
0.8.
Yeah, 0.8. Again, I could write 0.8, but if I write 0.8, then I'm losing the like pattern recognition. So how could I really think about this point more like generally? Like, sort of like what happens, how do I get from one of these to the next? Like think like computer science wise, yeah. Yeah, he's just like, dude, what's really happening here is each time when I go from one point to the next, I'm like incrementing by 2/5, right? So yeah, in fact, we call that delta x. We say that the delta x is 2/5 in the sense that we're like scooting over by 2/5 each time. So if I want to kind of write this out in a way that's going to generalize, instead of calling this 4/5, I'm going to call it 2 times 2/5, f of 2 times 2/5. Everyone with me? All right, and then this point we would say is like 3 times 2/5, because now by the time I get here, I've scooted over by 2/5 3 times, f of that. And then 4 times 2/5, f of that, and 5 times 2/5, f of that. Okay, cool. Good. And if I want to be like really sort of obnoxious about this, I can even this 2/5 I can even write as like 1 times 2/5. Just so now that there's like a clear pattern, which is that each time I'm just incrementing by like 2/5. Okay. Good. Let's now write a formula for the area then of the sum of these 5 rectangles. So let's just like start over here and let's all do it. Jordan, what's the area of the first rectangle? Yep. The width of the rectangle is 2/5, and the height of the rectangle is f of 1 times 2/5. Next, Nike, second rectangle.
2/5 times f of 2 times 2/5.
Yeah, of course, the second rectangle, even though 4/5 is the point we talked about, the width of that rectangle is still 2/5, right? Okay, good. One more. Yep. And like a certain kind of brain is like already getting sort of bored, right? Because we're writing the same thing over and over again. And I'll do the last one, or the second last one.
2/5 times 4 times 2.
Yeah. Okay, and I'll do the last one. It's 2/5 times f of 5 times 2. Okay, but like this is exactly what we invented sigma notation for. So we wouldn't have to like tediously write out expressions like this. So let's do it. Rebecca, please express the sum of this area in sigma notation. And notice how, it's just like, it's like a sequence, right? And what's changing in the sequence each time? Well, it's like that's the number that's changing, right? So like that's like kind of what we want to increment each time is like how much we scoot over by before we plug it in. Where do we start? Where do we end at? Yep. Everyone cool? It's just totally natural. It's just simply taking that summation in which there's an obvious pattern, which is that we're incrementing by 1 each time, and just expressing it in sigma notation. Notice how she also sort of like factored the 2/5 out from all the things and sort of took it right out of the sigma. Are we good? Okay, now again, because there's only just 5 rectangles, we could probably just like do this just by just crunching the numbers really fast, but that's like sort of not the point. So alright, so let's keep going. So what do we get here? We get 2/5 times, well, now it's time to finally start actually using the fact that we know what this function is. It's negative x squared plus 5. So evaluate, like plug this expression into the negative x squared plus 5 function so that we can figure out what it is. You guys with me? So it's like negative 2/5 I squared plus 5, like that. Alright. Now we just have this kind of like ugly sigma notation thing to work out. Any recommendations? Just kind of like expand stuff and just see what happens. Alright. So I get 2/5 times the sum from I equals 1 to 5. And then this is going to be in the brackets, it's like negative 4/25 I squared plus 5. Not doing anything like deep or cool or anything, we're just kind of like doing it all out. Any other suggestions now? Yeah, Noah.
I guess you can bring in the 2/5. That kind of makes
Yeah, you could bring in the 2/5, but then what? How are we gonna ever compute this? Does it look like something we maybe like know? Naveen knows. Naveen.
You can plot the 5.
Okay. Okay. Yeah, good. Naveen's like, dude, we did this whole thing back in pre-calc C where we learned formulas for like the sum of the squares. Flip the camera over here. Let's do a quick review of this. What is the sum from I equals, you can just spin it, yeah, from I equals 1 to n of like I? In other words, what's 1 plus 2 plus 3 plus 4 all the way up to stopping at n? These are formulas. We discovered them, proved them, derived them, inductioned them, looked at pretty pictures. Yeah. Okay. The one that I actually care about for the purposes of this problem is the sum from I equals 1 to n of I squared. So that's like 1 plus 4 plus 9 plus 16, etc. all the way up to we stop at n squared. What's that? Who remembers?
n times n times 1 times n times 2 over set.
Close. N plus 1.
And then
Oh,
plus
yeah,
two.
yeah. I meant plus 2 or no?
2n plus 1?
Yeah, 2n plus 1 over 6. That is the formula. Find the pretty packet with dots all over it, and you can remember why that's true. Good. We even went up further, right? We went from I equals 1 to n of I cubed, which is this is just like the square of that one. Remember? So this is like n squared, n plus 1 squared over 4. And that's a thing that hopefully should ring a bell. And then, okay, this one's like too silly to even mention, so I mention it. If I add 1 n times, then okay, good. So knowing that I have these formulas means that I should like try to maybe like treat like the sum of the squares and sum of constants like independently. But yeah. So what I'm gonna do is, can you guys handle doing this all at once? Like we're gonna split up this sigma into 2 sigmas. We can do it in 2 steps. We can split up this sigma from I equals 1 to 5 up into the negative 4/25 I squared plus another sigma which is I equals 1 to 5 of 5. See what I'm doing? And now I can, in each of those, I can like factor out the constants. And so then I really have like treated them each like separately. So what I really get is, what's the outside the first one? This would be like negative 8 over 125 sum from I equals 1 to 5 of I cubed. With me, everyone? No, not I cubed, I squared. Yeah. And then this next one is, again, pulling out the 5, it cancels the 2/5. I think we just get 2 here, right?
10.
No,
You've got the
2. Wait, what was
Yeah,
I wrong?
some one, so
No.
I think it's just.
Yeah.
You
2
like-
times, oh no, sorry. I didn't finish writing. 2
Okay.
times the sum from I equals 1 to n of 5, which of course is just 10. Yeah. Alright, does everyone see what I did there? I first split up this sigma into 2 sigmas, which is allowed because of course it's all just properties of the, so it's all just the associative property of addition in weird ways, right? If I'm adding up 5 times a pair of things, then that's the same as just adding up the first thing 5 times and then adding up the second thing 5 times. And then by splitting it and factoring out the coefficients, I now have these kind of expressions. And now I can just use this formula. So I get negative 8 over 125 times, what is the sum from I equals 1 to 5 of I squared? Of course I can just do this even if I didn't know the formula, but I do know the formula. It's 5 times 6 times 11 over 6. Okay, and then as some of you were just telling me already, if you add up 1 5 times you get, wait, this should just be a 1, right?
Yeah.
Does that make sense now?
Yes.
Okay, good. So add up 1 5 times, so that's just 10. Okay, so again this is tedious. We could all add up the squares from 1 to 5 faster than we did it by formula, but okay. So we can cancel the 6, we can cancel the 25. So what I guess I get is negative 88 over 25 plus 10. I think that is correct. And I could even write this as like 250 minus 88 over 25. So that's like minus 50 minus 38. So 162 over 25. And that's like, what is that? Goes in like 6 and some change. So that's 6.48. Okay. We have accomplished something. We have decided that the area under that curve is approximately 6.48. And in particular, it's more than 6.48. Okay, second half of the page, going a little faster. Now I want an upper estimate. So draw some rectangles so that we get an upper estimate and start cranking.